So we're going to start our discussion on columns by talking about an ideal column. And there is a little bit of terminology that we need to go over first. And so by definition, a column is a long, slender member that supports a compressive load. And typically, where you're going to see this in architectural structures. I'm sure you can go into a parking garage and you'll see that concrete pylon that's sitting there supporting the weight of everything that's going on. And so this is under pure compression because the weight of the floor above it is pushing down on it. So what we care about being strength of materials comes down to how is a column going to fail? And there's three different ways that a column can fail. The first is, with what we've been doing, the compressive stress applied to the column can exceed the yield stress of the column, or the ultimate stress in the column. So your compressive stress can be greater than the yield. Typically, when we're dealing with materials, why do we use yield? Why do we not use ultimate? Remember, yield is where we start going from that elastic to plastic behavior, and especially if you go into the strength materials lab and you're doing the tensile test with the dog bone, once you get past yielding point, it's going to fail at that point because you've already started to change things. Everything's just going to keep snowballing. It's eventually going to fail. So we consider a column failing via material when its compressive stress is greater than the yield stress, because the material is just going to rip apart at that point. And that's all that's going to happen. It's going to break. It's going to collapse. The second thing is that if we apply a load large enough to the column, we're going to get a lateral or sideways displacement. So if I take a look at this bar here, I can keep applying a load here that eventually the column will bow. It'll have some sideward displacement that we refer to as delta. And so delta is that sideward displacement. Now we call this, when this happens, this lateral shift is called buckling. And so buckling leads to sudden and dramatic failures because once you move this over a little bit, what happens? Now you've got this load pushing down, and it's no longer an axial load. You've got a combined load where you've got bending and axial going on at the same time, and it's just going to completely and utterly collapse. And this is important. So you can have this happen in one of two things. So if I'm looking, let's say that, I don't know why my pen's not working now. Okay, now it's working again. So here's my eyeball. If I'm looking on it this way, let's say that's the cross section. So looking down on top of it, and we'll say, well, this is the y direction, this is the x direction. So what could happen is you can get the lateral shift in one of two ways. You can get it in the x direction or in the y direction. And that's the other two modes of failure for buckling, because it can sit there and it can buckle in the x direction, it can buckle in the y direction. So those are the three ways that the column can fail. It can fail because of material, it can fail because of buckling in the x, and it can fail buckling in the y. This is an important thing to note because typically especially when you're doing column problems, you have to do all three. Because if the material fails before it buckles in either direction, it's going to have a material failure. If it doesn't fail, then it's going to buckle in the x or the y direction. And, just a little note, that's the kind of stuff that I like to ask on tests, is which of these three modes will it fail? So we can either have it fail by fracture or yielding, which is our material failure. We can have it fail by buckling. Where we get to that buckling, when the load is just on the verge of buckling, to where we get to the point where if we add just any little bit more, it's going to buckle, we give that a special name, and we call that the critical load. So the critical load is right on the verge of failure. If you load a column up to the critical load, you get a sideward displacement, and it fails. Now, how do we calculate out that critical load? So we calculate out that critical load by using the equation of the elastic curve. And I know, especially this semester, because of being an online class that wasn't prepared to, and we lost a week in the semester, we did not fully do the equation elastic curve via the calculus equations. So we're just going to kind of skip that part, and we're going to get right to the actual equation itself, which we could use the equation elastic curve and solve for what the deflection is going to be. And so this gets a little bit on the mathy side, so we need that there. So what we have is the second derivative of the displacement plus the displacement times this load over EI. Remember, EI is our modulus elasticity and moment of inertia. That all equals 0. So the important thing about this is this may or may not look familiar to you. This is from differential equations. This would be the differential equation for simple harmonic motion. And so then if we go and solve that, and to keep you from skipping this part of the video, because I know that you're not really interested in the math behind it anyway, we're just going to get to the solution. Now, the solution for simple harmonic is a combination of sines and cosines, because it's the definition of a harmonic. So if we look at that, we would say V a sine px plus b cosine px. And so what this is going to do is we have a bunch of boundary conditions that we can apply. Now this one's important. So we're looking at a ideal column. So we're going to assume that we're pinning it at both ends. And that's an important place to start, because if we don't make that assumption, we have a different equation. But right now, the ideal column pinned at both ends, which means that we're going to have no vertical displacement at the top or the bottom of the column. So any of the displacement has to happen in the middle. Using those boundary conditions in this solution of the simple harmonic, we're going to get an infinite series of solutions that will solve it, because that's what a harmonic does. Since it sits there and goes like that, you have an infinite amount of solutions along this that will solve the problem. But since we're looking at where it fails, we're looking at the smallest of those solutions. So the critical load, the smallest of these solutions, can be solved by saying pi squared EI over L squared, where L squared is the length, the height of our column. You should box this equation. You put 2 boxes around it, 3 boxes around it. This is the most important equation that you will have for a column. Now, the important thing to remember is this column is pinned at both ends, and that's going to become important as we talk about the next topic, but let's not worry about that now. So this is Euler's formula. EULER, the same guy from calc or whatever, very famous Swedish mathematician, 1707 to 1783. And so Euler's formula only applies when the critical stress is less than the yield stress. Why is this important? Because if the critical stress is higher than the yield stress, that means that this is failing, the material's failing before it has a chance to buckle. So how do we define the critical stress? We'll leave it on this page here. So critical stress, just the critical load over the area. And so if I want to plug all that stuff in, what I end up with is pi squared times E, the AR squared, and I'll explain that R in a second, over AL squared. And so this would be critical stress. You're going to go and solve it from this equation. I wouldn't. I would just take your critical load and divide it by the area. But if you want to plug all this stuff in, this brings up a new term here, this R, which we call the radius of gyration. This is some information that could be given to you at some point. So what is the radius of gyration? The radius of gyration is going to be defined as the moment of inertia divided by the area, and you're going to take the square root of that. Now, typically what you'll see is you will see this plugged into tables, because since moment of inertia and area are both geometric properties, it's something that you can look up for certain cross sections. Now, this is important because we can rearrange that critical stress equation then using everything and go, the critical stress is equal to pi squared E divided by L over R squared. And this is important because in columns you will see L over R come up, and that's defined as the slenderness ratio. And as we can see here, we've actually got a table here that gives us the slenderness ratio over the critical stress. And so if you know the slenderness ratio, you can just go right on this column, right on this chart, and figure out what the critical stress is going to be. But the important thing is still going to come down to, and basically everything that we're going to do with columns is going to come down to this right here, Euler's equation. Here's my star, you triple boxed it and whatnot. And this is only valid when the critical stress is less than the yield stress. Now, the important thing is I just listed out the moment of inertia, I. Well, we've got an IX and an IY. What the moment of inertia in the X direction is, what it is in the Y direction. The critical load is going to refer to the least moment of inertia, which means that you're going to have to solve for both moment of inertias I and X. And whichever is smaller, that's the direction it'll buckle, because it's going to have a lower critical load to buckle in the smaller direction than it would the larger direction. And so obviously it's going to fail in the smaller direction before it ever has a chance to fail in the larger direction. So once again, the takeaway from this lecture, Euler's formula. This is for an ideal column that is pinned at both ends.